Assalamualaikum warahmatullahi wabarakatuh. So for today, we are going to discuss several questions regarding the gas absorption process. Starting from this first example in your slide, okay. This is the case study, a very simple case study on how we want to calculate the um, concentration of the oxygen dissolved in water, while the question give you the value for partial pressure as well as the Henry's law constant. So as we have learned in the previous session, we have learned on the equation used for the Henry's law relation, which is PA is equals to HXA. So by taking or by using this equation, actually we can calculate the mole fraction of a liquid in the mixtures, which is XA, by manipulating this equation. So what you need to do is just to substitute the values question give you in the question, uh, which is PA. The question give you the partial pressure is 0.21. Actually this is small p, okay. Small pa is equals to h small xa. So this small pa, okay, partial pressure of component A, the question gives you 0.21, and it is equals to the h value is given 4.338 multiplied to the 10 to the power of 4. So substitute in here and you find the value of x. So very easy application. Then you can get the value for xa, which is the concentration of water for the system. Okay, let's move to the next example in your slides, which is this example is refers to the solving a case study for single stage gas absorption process. Starting from the first sentence, okay, a gas mixture at 1 atm pressure absolute containing air and CO2 is contacted in a single stage mixer continuously with pure water. So how does we know this example is refers to the gas absorption single stage? You need to find a keyword here, which is the keyword is if you find out, okay, this system consists of three components, which is uh, air, CO2 and pure water. So it means that uh, it is belongs to the gas absorption. To prove it right, okay, we to prove it right, we see, okay, in the next sentence it refers to the gas flow rate. Inner gas flow rate, as well as it shows there is a liquid flow rate. So it's a um, gas and liquid flow rate, and it says that it reached equilibrium. So this all of this info is refers to the single stage gas absorption, and to be clear about it, okay, the last sentence is it needs you to calculate the amount of composition of two outlet phases, okay, which means the question does not ask you on calculate the number of stages, calculate the height of the packing. So meaning it refers to the single stage gas absorption, because for the single stage no need for you to calculate the number of stages because it's just one stage. And normally for single stage we just need to calculate uh, the the amount of composition at the outlet phases. That's it. Okay, so based from this question, calculate the amount and composition of two outlet phases refers to the single stage gas absorption process. The other name for single stage absorption process is single stage mixer. Okay, so this is just the other name of the single stage gas absorption column. So after we know that this system is the single stage gas absorption, what we will need to do is to uh, uh, draw the diagram, okay, of the gas absorption. Okay, so we draw the diagram of the gas absorption. Actually I already simplified to you the diagram for three types of gas absorption, but I will simplify it again only for single stage. So this is single stage absorption, and for gas absorption, it contains a four main stream, okay, which are inlet, inlet gas, outlet gas. So gas normally flows from bottom to top, and we got inlet liquid and outlet liquid. So the liquid will flows from top to bottom. So based from this direction, it is counter current mode of operation because the different in direction of gas and liquid flows into the column. Next is to write down the denotation of these streams. So for a single stage, the inlet gas will be V naught, sorry, V2, okay, and the outlet gas will be V naught. And for our liquid inlet will be L naught and the liquid outlet L1. Okay, and then we got the mole fraction for each and every stream. For this one, for inlet gas, there will be, because it is gas stream which is V, so uh, the the mole fraction will be stated as Y, and since we got three components in the system, so there must be three mole fraction, whether it has a value or not, that will be the number 2. Okay, so you just write down the denotation first. It is YA, YB, and YC. And for this stream number 2, so you write down this is number 2. So this is subscript. Okay, and move on to the gas outlet. So the gas outlet, the mole fraction is also Y, so it would be Y A, Y B, and Y C. And this is stream naught, so just write down like naught. Okay, so sorry, so this is subscript. Okay, so this one is L, so liquid, the mole fraction will be X, A, C. So this is stream naught, so write down naught, and this will be and last but not least, this one. Okay. Okay, so after we draw the diagram of the gas absorption for a single stage, together with the denotation in the system. So the next step is to extract the info from the question into the diagram. So starting from the first information is stated, it's stated the system is operated in one ATM. So we know it is one ATM, and we got three components here, which is component number one, which is air. Component number two is is the second component is CO2, and the last component is pure air. So normally, how we can identify which component will be the component A is the component that want to be absorbed will be the component A, which is here. Uh, Air and CO2 is contacted in single stage mixer with the pure water. So the pure water will be the solvent, and the pure water need to be used to absorb CO2 from pure air. So CO2 will be your component A. Okay, and then if you want to know that why CO2 will be component A, you will find out in the last sentence, as the question asks you to make a balance on CO2, and also is stated here component A. So CO2 will be our solute or the desired component, or our absorbed component. So CO2 will be A, pure air will be B, and water will be C. So water are going to be used to absorb CO2 from pure air. Okay, so as we know, the component A is the CO2, component B is pure air, and component C is the water. Okay, so this is carbon dioxide. Okay, so next is to uh, extract the info starting from this sentence. Okay, it stated the inlet gas flow rate is 100 kg/mol per hour. Okay, so inlet gas flow rate, regarding or referring to this diagram, inlet gas flow rate. So inlet means the direction will be go into the system. So this two is inlet flow rate. So which one is inlet gas flow rate? Gas. So gas is refers to the vapor stream. This is liquid stream. So this will be the inlet gas flow rate, which is V2. So the question give you the value for V2. Inlet gas flow rate is 100 kg/mol per hour. So you write down here. Okay, 100 kg/mol per hour. So this is the value for V2. Okay, V2 is 100 kg/mol per hour. And next is with a mole fraction of CO2 0.2. Yeah, but in the same sentence, okay, meaning this fraction is refers to the fraction that contained in the inlet gas flow rate. So they give you the mole fraction of CO2, okay, which is 0.2. So we know that CO2 is A. So referring to the inlet gas flow rate, the question gives you the value for Ya2, because it is component A, carbon dioxide. Okay, carbon dioxide, a mole fraction of CO2 is 0.2. So this will be 0.2 mole fraction. The next information the question give it to you is the liquid flow rate entering is 300 liquid flow rate. So liquid flow rate is your solvent, flow rate entering. Entering means inlet. So inlet liquid. So referring to your diagram, inlet liquid is refers to L naught. So L naught, the question give you 300 kmol per hour. Okay, and then the question stated about pure water or pure solvent. So when it stated pure water or pure solvent, okay, water is the solvent, so the word pure there, actually we can put a value here. Since it is pure, meaning 100% of water is going to be used for the system to absorb carbon dioxide from the air. So this will be pure water. So if pure water, meaning the water is C, so in the inlet liquid or inlet solvent, uh, we know that Xc naught will be 1 because 100% of water is C, is going to be used for the system. Okay, so 1 is refers to mole fraction 1 is refers to Xc naught. And since we know this is 1, so the rest of the values here will be 0. Why 0 is because we apply the same fundamental is the according to Dalton's law, the summation of the mole fraction uh, for all of the components in a stream, for example in a system, is equals to 1. So the summation of xa naught plus xp naught plus xe naught is equals to 1. Same goes to mole fraction in this stream, same goes to the mole fraction in this stream, so same goes to the mole fraction of this stream. So the summation of all of these must be equals to 1. So since you already have the value for Xe naught, which is pure water, is equals to 1, so the rest will be 0. And next is since over here is pure water, and of course in the vapor stream, which is V2, uh, liquid is in liquid solvent is in liquid phase. So in vapor phase, it's only appears only vapor component, so or a gas component. So over here, okay, it is A is refers to CO2, which is in terms of gas. So C here, water, will be definitely will be 0 because C is the solvent and the solvent is water. Water is in liquid form. So in liquid form, it does not exist in the vapor stream. Okay, so it will be 0. So the rest value, which is YB2, we can find out the value by uh, minus 1 minus with 0.2, which is equals to 0.8, because the summation of this fraction must be equals to 1. So 0.2, 0.8. Same goes to this one. Actually, the value for YC not is equals to 0 because the water, which is in liquid phase, does not exist in the gas stream, which is V naught. So this is gas outlet stream. So we only have the value for YA naught and YB naught. Although the question did not give you these values, but we know, okay, this is the value that we can put in the diagram. Okay, and then according to the question, they ask you to make a balance on CO2. Actually, whenever you want to calculate and the amount of composition, uh, automatically you will do the balance. Okay, so calculate the amount and composition of two outlet phases. So outlet phases means, okay, the question asks you to find the outlet phases is refers to V naught and L1. So they ask you these values and also these values, which is V naught and L1, and composition of outlet phases, it is refers to the YA naught and also XA1. So this is the question aim to ask you this V naught, L1, YA naught and XA1. Okay, so why you just need to calculate for YA0 and XA1 is because that is our aim, where A is the harmful gas, which is CO2. So the aim is to calculate or need to get the values for the harmful gas composition at outlet phases. That's why we want to calculate for YA0 and XA1. Okay, so in order for us to calculate for V0 and L1, we need to first solve for YA0 and XA1. So we assume that to get the YA0 and XA1, okay, by ignoring first the V0 and L1, to get the YA0 and XA1, it will be two unknown. So if two unknown means we need to use two balance, okay, two balance. So the balance is the material balance is first that we can use is material balance for single stage. Okay. So how can we find this material balance for single stage? Is from your appendix. So I already attached you an appendix in your VLE, and you refer to the chapter 2 absorption process. Okay, and here you see there are three three long equation. So this is refers to the material balance for gas absorption for three types of gas absorption. Okay, the first is for multi-stage gas absorption, because multi-stage we got several stage, so the stage is refers to n, so this is refers to the multi-stage. The second one is for packed absorption column, because it does not have knot and it does not have n, so it's just content of 1 2 1 2. So we reflect to the material balance or the diagram of the packed absorption column. So the second equation is refers to the material balance for packed, and this last equation, okay, we are going to use this equation to solve for single stage gas absorption column, because it contains of knot 2 1 1. So how can we know this is belongs to the single stage? Knot. Okay, so we refer to this stream. Okay, it contains of knot stream. This is knot. Okay, and then it contains of number 2 and number 1 stream. 2 and 1. So 2 and 1. Okay, 2 and 1 stream. Okay, and it does not contain of n. So if there is no n and there is no uh, if there is no n and it contain of knot, so it refers to the single stage gas absorption column. So by using this equation, okay, by using this equation, okay, which is this one, okay. So you need to write down this equation on your paper, and you need to substitute the information in the equation. But before that, okay, from this equation, you see there is a L prime and V prime for X naught, XA naught, YA2, XA1, and YA1. There's no problem because all of that values already have in the diagram. Okay, but before that, okay, this is XA, right? So if you refer to the equation here, okay, I already put as XA, but some of the book also can also state it is just X naught 1 over minus X naught. So if you want to do the balance for component A, so you write down A, all are in component A. But if you want to do balance for component B, it will be XB naught over 1 minus XB naught. Okay, this one also YB naught over 1 minus YB naught, and so on. But normally we will do only for component A. Okay, so like this lah, like this equation. Okay, so as in here, Okay, in this equation, we need to know the value for L prime, and V prime. So we know that this L prime is liquid inert. It is the same value as L naught as well as L1. Liquid inert or solvent inert means the amount of solvent that enters into the column, which is 300 kmol per hour. We assume there is no loss of solvent throughout the process, which is if the solvent enters into the column 300 kmol per hour, so the outlet solvent flow rate, which is L1, will be also around 300 also, because we assume there is no loss in solvent. Okay, so this L naught is also named as L prime, the same value as L prime. L prime is refers to the inert solvent. So as we have the value for L naught is 300, automatically the L prime value will be 300. Okay, 300 kmol per hour. And if you refer to the equation here, okay, as we know this is L prime is 300, and you can substitute the value for 300 over here and 300 into in this equation. But how to get the value for V prime is stated here. Okay, so this V prime, the definition of V prime is the inert inert pure air flow rate, okay, or inert air. So V prime is actually inert air flow rate. The name is air, uh, inert air, okay, which is air is our air is refers to the pure air, which is V. So by right, it is the same as the value for VB2, which is VB at stream number 2. Okay, VB at stream number 2, and is also same value for VB naught. Okay, VB naught, which is stated here. Okay, over here. So meaning V prime will be exist in inlet gas stream, and also it will exist in the outlet gas stream, and the value for both will be similar. So VB2 is meaning that the total flow rate, which is V2 multiplied with the mole fraction of YB2, it is equals to VB2. V naught multiply the value for YB naught will be equals to VB naught, which is if you summarize here, the VB2, the name is the flow rate of pure air, or our component B, in the stream. And for VB naught, it is equals to flow rate of pure air, which is component B, in outlet stream. Okay, flow rate of pure air B in inlet stream, inlet gas stream. Okay, outlet gas stream. Alright. So these two value VB naught, VB2 and VB naught values is equals to the V prime, and it will result the same answers. So if you get V prime here, you can use this value to be used in V prime in the outlet gas stream. So that's why in here, when you get this value, okay, you get 80. So you can use to put V prime here and V prime over here, 80 and 80. Okay, so based from this diagram, the enough information to calculate for V prime is from the gas inlet stream, which is we already have the value for V2 and YB2. Okay, so if you refer to the appendix, in the appendix also stated how to calculate the V prime value, which is V prime is equals to Vn plus 1 multiplied with Yn plus 1. Actually, it is the if you use for the single stage, this n will be replaced as 1. So this Vn plus 1 is V2. So V2 is the stream here. This is V2. Okay, and this yn plus 1, so n is replaces 1 because we use for single stage, so n is equals to 1. So this will be y1 plus 1 is y2. So for component a, so it will be ya2. So ya2 value, this is value ya2 is 0.2. Okay, so if you can copy this equation on this. Alright, so this equation, we make it larger. Okay, so Vn plus 1, yeah, Vn plus 1 is the V2. So this will be V2, okay, multiply with 1 minus Yen plus Yen plus 1. So it will be 1 minus 0 0.2. 1 minus Yen plus 1. So n plus 1 will be n will be 1. So 1 plus 1 will be 2. Okay, so this will be ya2. So this is the value for ya2. So this is subscript. Okay, so this will be ya2. And it will be, we simplify, it will be V2 is 100 multiplied with 1 minus ya2 is 0.2. So the answer is like in here, okay, 80. Or in other words, okay, this is actually V2 multiplied with the mole fraction of component B, because V prime is refers to inert air. Air is the component B, pure air. So of course the total flow rate V2 multiplied with the mole fraction of pure air, which is YB2, is equals to the V prime, which is the V inert. So it is also similar when you calculate for YB2. You will get the same answer. Okay, so this is how we calculate for V prime value. So as you know, okay, this 80 is your V prime value. So you just need to substitute this V prime inside the material balance for single stage gas absorption that you already take from your appendix. So put the 80 value in here and in here. So XA naught from the diagram, we know the XA naught is equals to 0. Okay, yang ni. Okay, this one. XA naught is 0. So substitute in this equation, XA naught will be 0, 0. YA2 from your diagram, YA2 is 0.2. So 0.2, substitute in here, 0.2. XA1 and YA1, actually we don't have the value. Okay, XA1 and YA1. Okay, we don't have the value. Okay, so let it be the unknown. Okay. Oh, I do the mistake. Okay, so this is V2. Okay, that go out from the system is V1. Okay, so this is stream 1. So this will be 1. Sorry, for not is refers to the and okay, B1. This is 1. So this will be 1, YB1, YC1, and okay, this one, right? So sorry about that. So we need to calculate for YA1 and XA1. So from this equation, okay, so since XA1 and YA1 we still don't have the value, so let it be unknown. Okay, so we got two components or two unknown, so meaning we need to get two equation. So this equation is, we call it as balance for CO2, which is we already answer for the for this. Okay, make a balance on CO2. We already done it by using material balance of single stage gas absorption column. So the next is to find out another one more equation that relates with the uh, relate with this one, XA1 and YA1. So we got another relation, which is by using Henry's law relation, where Henry's law relation, it has the if Henry's law relation, if you recall back in the slide, okay, the the relationship is partial pressure of A is equals to Henry's law multiply with XA. Okay. Another one is whenever we divide this PA with pressure total, it will be PA over P total. So it will be like this, over P total is equals to H must divide with P total also. Okay. And this will be multiplied with XA. So when we simplify PA over P total, it will be YA is equals to H over P will be written as H prime. Okay. And it multiply with XA. Okay, XA. Okay, so since in a material balance previously, we need to calculate for YA1 and XA1. So based from the carbon dioxide material balance, we left the unknown, it will be YA1 and XA1. So based from this last equation by using Henry's law relation, we can see there is a relationship between YA and XA with the Henry's law relation. So if we want to calculate for YA1 and XA1, so you just write down this will be YA1 and XA1. So we can use another relationship of YA1 and XA1. So our aim is to find the value for H prime to get one equation, to use this equation to solve simultaneously with the previous equation, yeah, material balance. So our job is to find the value for H prime. Okay, H prime values. How can we get the H prime values? Is by from the properties table of Henry's law. So the question gives you this table. So this is the Henry's law table. So as the question, the solute or the harmful gas is CO2. So we need to refer to the column for the CO2. And you see this is the temperature, right? So the temperature is the operating temperature. So you see the operating temperature for the system is 293K. So 293K is somewhere here in the middle of these values. So actually to get the accurate value, you need to do interpolation. Okay, which is interpolation. By using interpolation, you will get the correct value for the H value for the condition of 293 for component CO2. But for this question, it's just use the value for simplified, which is 0.142. So after this, I will show you how to do. Okay, so how to do the interpolation, which is the question give you the uh, the uh, the the temperature condition is 293 K. Okay, so this is for recap from the question, and according to this column, yeah, how to do the interpolation. Actually, you already know this how to do the interpolation, right? But I just need to want to give you uh, the revision on how to do the interpolation. So here, just write down 283.2. So our K value is 293 K. So from the table, the next temperature is 293.2. Okay, so this one for the component of CO2, the value for 283.2 is 0.142. So the H value for 293, which is here, we want to get this value. Okay, and for 293.2, based from this 280, oh sorry, so this one is 0.104. Okay, so for this one, 293.2 is 0.142. Okay, so this is the unknown, where the H prime is the unknown. So how we do the interpolation to get the value of H at the temperature 293 K. Okay, so the simplest method is you write down 293 minus 283.2. Okay, this one, this value minus with this value over the last value over the first value. 293.2 minus 283.2. This one is equals to as this one is 293, so this is H prime. Okay, so you write down here H prime. This 293 is here, right? So this is H prime. This 293 minus with 283.2, so H prime minus 0.104. 0.104 over this 293.2 is refers to 0.142, so 0.142 minus this 293.2 minus 283, so this one, so 0.142 minus 0.104. Done. Okay, so you just solve for this equation. Okay, you will press your calculator and you find out the value of H prime. So that is how we do the interpolation. Okay, okay, done. So for example, okay, when you get the value for H prime, the next step is, okay, for let's say your value is, the value for H prime is we just take like this one, okay, 0.142. Okay, you get the value for 0.142. Go back to this table. Okay, you don't forget to multiply with 10 to the power of minus 4. Okay, so this is the value. Okay, for example, we got 0.142. Okay, but don't forget to multiply with this exponential part. Okay, but okay, in the table is stated 10 to the power of minus 4, but in real, okay, in real thing, you need to multiply with 0.142 multiply with 10 to the power of 4. So the negative sign here, you just ignored. Okay, that is the fundamental or rules of thumb, if I'm not mistaken. Okay, so this one will be 0.142 multiplied with 10 to the power of 4. And don't forget to write down its unit, which is ATM per mole fraction, which is in terms of ATM. So from the table, we got the Henry's law value, the H. But in the solution, or in our, as we want to solve for this one, we want for H prime. And we know the H prime is equals to H over P, which is stated here. Okay, H over P is equals to H prime. So from the table, we get the value for H. So we need to divide with the pressure total, then only you get the value for H. So according to this solution, H prime is equals to H over P. So this is your value for H prime, where you get from the table. You divide with the pressure total. So the pressure total given in the question is 1 atm, so supposedly you will get the same answer. But if the pressure total from the question is not 1 atm, like 2 3, so this value will be different. So by right from the example, they give you the pressure total is 1 atm, so should be no problem. The value will be similar to the Henry's law value. Okay, so your value for H prime would be 0.142 multiplied with 10 to the power of 4. So once we know the value of H prime with this value, we substitute into the equation that we put in here. Okay, this equation, y is equals to H prime xa1, which is as this one. So we just substitute this one to be the value of H prime. So this will be your equation number 2. So as according to the previous balance, okay, from this balance we get the value, or we get the equation for balance for component A. Okay, which is this one. Okay. This is component A. So equation number 2 or equation number 1. So this the first equation is equation number 1. Okay, so in terms of SA1, so you get one balance, and then you get another one more, equation number 2, which is by using Henderson relation. The unknown is also YA1 and SA1. So you got two unknown with two equation. So solve it simultaneously. So you just write down in your type in your calculator, or you want to solve it manually. Finally, you will get the value for XA1 and YA1. Okay, so this is the answer. So you can try this at home. And then don't stop at this point only, because you just actually by right we already have the value for YA1 and XA1, but the question also asks you to find the value for V1 and L1. So how to get the value for V1 and L1? So according to the appendix, okay, so if you want to get the value for L1, okay, this one, by using these two equations, if you want to get the value for L1, so n is replaced with 1, so L1 is equal to L prime over 1 minus XA1. Okay, if you want to calculate for V1, so this will be V prime over 1 minus YA1, which has been simplified in this slide. Okay, these two equations, so this we get from the appendix. So whatever value that you get as a1 and ya1 from the equation that we solved previously, xa1 and ya1, you substitute into the final equation, and then this L prime, we use the same answer, we use the same values, 300, and V prime, we have calculated for V prime previously, which is 80. Then finally you will get the value for L1 and V1. Then only you solve for all of the unknown that the question asks you, V1, L1, YA1, and XA1. So that's it for this case study of single stage gas absorption. Okay? They just want you to find the value for outlet phases for gas stream, and as well as composition at outlet phases. So we have done to discuss the case study for single stage gas absorption column.